in the 45th lecture, let us discuss about the carbon dioxide capture and storage and removal technologies. So, we have been discussing this week about various climate technologies. We discussed about the technologies on mitigation, on adaptation. We also discussed about the cross-cutting technologies. And now, in this class, that is the fifth class of this 9th week, let us discuss about the carbon dioxide capture, removal, capture, storage and removal technologies. So, through this, we will go through, to understand this, we will go through the following concepts. The concepts are carbon dioxide capture and storage in terms of CCS, we abbreviate it. Sometimes we abbreviate it as CCUS, carbon dioxide capture and capture, utilization and storage. And then we also try to discuss about the various components of this CCS technology. We'll also talk about the geological and storage and geological and ocean storage options, two important storage options after capturing the carbon. And the next point we will talk about the direct air capture. The third is we will also talk about the bioenergy with carbon capture and storage. We call it BECCS. So, essentially, we are going to talk about the carbon dioxide removal technologies. That means it also includes the capture and storage. So, we capture from atmosphere, store it somewhere else. We remove from the atmosphere, and either we utilize or store it somewhere else. So, essentially what we are talking, what we want to understand here, friends, we are bothered about high amount or more amount of carbon dioxide, what is there available in the atmosphere. So, as far as the carbon dioxide concentration is concerned, if you go back to some of our initial classes in the class week 1 or 2, you will realize, you will recall that that in last 50 years the carbon dioxide concentration in terms of ppm has increased very fast. In over past 50 plus years, it has reached from 365 ppm to about 425 ppm in current age. So, that means when we talk about the CO2 rise or the concentration of carbon dioxide rise in the atmosphere, and we all understand that carbon dioxide is one of the important greenhouse gases which traps the outgoing outgoing longer wavelength radiation. So, thereby it warms the atmosphere, and we also know that we need greenhouse gases, and we also have discussed that how much is the contribution in terms of greenhouse warming as far as the Earth's average temperature is concerned. We know that because of the presence of greenhouse gases, Earth's temperature is warmer by 33 degrees centigrade. That means had the greenhouse gases not been there in Earth's atmosphere, then Earth's atmosphere would have been cooler by 33 degrees centigrade, right? So, having recalled this discussion, we understand that we need greenhouse gases, and carbon dioxide is one of the dominant greenhouse gases. The second point is the reservoirs of carbon dioxide or carbon. You see, the lithology, the Earth's geology is the geological core, or the Earth core stores majority of the carbon. So, we discussed that if the total amount of carbon is supposed to be 10 to the power 23 grams in terms of budget, if the total amount of carbon is 10 to the power 23 grams, out of that 99.96% of the carbon is stored in the geological reservoirs. So that means whatever left is 0.04. So this 0.04 or O4 carbon, percentage of carbon, is equivalent to about 10 to the is equivalent about 40,000 petagrams. 1 petagram we know 10 to the power 15. So out of this 40,000 petagrams, 38,000 petagrams of carbon is present in the ocean. So that means next to the geological reservoir, the ocean is the second reservoir as far as the carbon is concerned. So the largest is the geological. The next to that is the ocean, and whatever is left over about 2,000 petagrams of carbon. Out of that, on the upper part of the crust or Earth's geology, what we say as the soil holds about 1500 petagrams of carbon, and another 560 plus petagrams of carbon is there in the biota, or you say in the plants. So this is a kind of broader budget as far as the carbon quantification and distribution is concerned in different reservoirs. So I'll just repeat. Largest reservoir is the geological sphere, then the ocean, then the soil, then the plants. But lot of carbon is present in the atmosphere. These carbon have been escaping from all or the rest of the reservoirs to the atmosphere. Rest of the reservoirs, that means from geological, from oceanic, from soil, and from the plants. So this is because of our activities. That means because of the activities of the human being, we say it because of anthropogenic activities. So this escape of the carbon dioxide from various reservoirs to the atmosphere is the cause of our concern, and it is actually leading towards warming or rising of the Earth's temperature. So after discussing various technologies for adaptation and mitigation, we also going to discuss today in detail what do we understand by carbon dioxide capture and storage. So that means we need to capture the carbon dioxide from various other sources. That means we will not allow this carbon dioxide to escape into the atmosphere. Okay. So that means we will capture it dominantly from the point sources or the industrial sources. So this CCS technology involves carbon dioxide capture and storage. Is a process which consists of separation of carbon dioxide from industrial and energy related sources. Why? Because large amount of carbon is emitted from these sources, from these industrial and energy related sources. So once we capture this, we can transport and store in other locations. As I mentioned, what are the other locations or the storage options we have? We have the other locations or storage option is the geological storage option. We also have the storage option, that is the oceanic storage option, right? So we transport to a storage location, and long term, that is how we isolate this carbon dioxide from the atmosphere in a longer term. Okay, so that means we are not saying that it is 100%. We are saying that long term isolation from the atmosphere, right? So what are the characteristics of this carbon capture and storage? The important characteristics are: capture of carbon dioxide can be applied to large point sources, as I just mentioned, with respect to industrial sources and energy related sources. The CO2 could then be compressed and transported for storage in geological formations. So once it is captured, it can be compressed because gas takes higher volume. If you compress, then the volume will be less. So it is compressed for transportation. it is transported for storage in geological formations or in the ocean. So let us understand, we'll see what do we mean by the geological formations, and also in mineral carbonates, or we utilize for various other activities including various industrial processes. So that means importantly we capture, then we compress to transport for storing in ocean, geological formations, and also in mineral carbonates, or we use it in industrial processes. That means the net reduction of emissions to atmosphere through the CCS technology, it depends on fraction of carbon dioxide captured, the increased carbon dioxide production resulting from loss in overall efficiency of power plants or industrial processes due to additional energy required for capture, transport and storage. This point actually talks about the energy requirement, because to capture this carbon dioxide, the industry or the energy unit or energy production unit per se, any industry unit will require more energy. So that means it is also an energy intensive process. It will also add to the budget in terms of capturing, transport and storage. And also the other side is there is also leakage during the transport, and also some fraction of carbon dioxide is retained in storage over the long term. So leakage in terms of transport and leakage, and also lot of this carbon which we store in the geological reserve, they remain there for longer term. So that is a big respite if we capture at various industrial sources and take and store it in the geological spheres. This particular diagram is useful in terms of understanding how the total story goes around. Looks like, if you see on the right hand side, that's the industrial unit, and all the arrows which are the red arrows, they talk about the collection of the carbon dioxide, and the blue arrows are talking about collection of this to the industries, and the blue is which is captured, which is captured, and after that it is transported, captured then transported for either storage in terms of mineral carbonation, or in oceanic storage, or in the geological storage. But also we can see some part of that is also utilized in various industrial processes. So this actually talks about the total concept, or the total story as far as the carbon capture and storage system is concerned. So as far as the components, we know in terms of the component and the technology, we can see here the left hand side, there are the capturing carbon dioxide capture component, transportation component, storage in terms of geological and ocean sphere, and also in the mineral carbonation, and also some industrial use. And the second column talks about various technologies. In terms of carbon capture, we can do it at post or pre-combustion stage. We can also do it using oxygen as oxygen in terms of oxy-fuel combustion, and then industrial separation in terms of natural gas processing and ammonia production. Coming to transportation, two ways this captured carbon is transported. One is pipeline, and the other one is shipping by using the ships. The storage option, first coming to the geological storage, we also have another figure to discuss in detail. So EOR, enhanced oil recovery, gas or oil field, the saline formations, and enhanced coal bed methane recovery, ECBM. Coming to ocean storage, direct injection in terms of dissolution type, direct injection in terms of lake type. Then coming to the mineral carbonation, natural silicate minerals and waste minerals, and also the industrial use component. The primary methods employed in capturing and separating carbon dioxide encompass various technology, pre-combustion, post-combustion and oxy-fuel. In terms of absorption, we can go for chemical absorption or physical absorption. In terms of membrane-based separation, because we need to separate carbon dioxide from rest. So that can be done through various technical means. One is gas separation. In terms of gas separation, absorption by various other gases, ceramic membranes, the polymeric membranes or hybrid membranes. So membrane based and gas based. Then coming to the adsorption. Adsorption is the absorption at the surface, all of us know. So it uses two methods, both chemical and physical. Whereas coming to the chemical looping, it also talks about the calcium and the metal oxide in terms of calcium looping and metal oxide. So moving on to the capture system, as mentioned before, you see at industrial separation level, industry processes, you separate the carbon dioxide graphics is mentioned. In terms of post combustion also, so air is required for combustion, so carbon dioxide is separated and also it releases some amount of heat and power. In terms of the pre-combustion also, using gasification and other reforms, the air and oxygen plus steam is required as input. So to produce that also we need energy and other things. So it releases the hydrogen and carbon dioxide which is separated. So carbon dioxide we take we compress and take it away, and hydrogen is produced which also can be utilized in some other ways. And oxy-fuel, you really use oxygen during combustion process. So oxygen is separated and produced, and then the CO2 is compressed and taken out for transportation, and also heat and power is produced. So in post-combustion, pre-combustion and oxy-fuel, everywhere heat and power is produced as byproduct, and carbon dioxide is compressed and taken for transport either by ship or by pipeline. And in terms of, now moving on, in terms of the storage options, as we know, as far as the overview of the geological storage option is concerned, look at the 4 different ways. So one is the depleted oil gas reservoirs. So the point number 1, wherever 1 is written, you can see there that here the carbon dioxide is used in terms of wherever the oil and gas reservoirs were earlier there, it has been extracted and now it is depleted. So that means there is some vacuum. The vacuum is lying there. So there, this carbon dioxide is compressed and put and injected there so that it lies there. It can, there is space, there is gap, so it can stay there. It can be stored there. So storage of carbon dioxide in deep onshore and offshore geological formation use many of the same technologies that have been developed by oil and gas industry and has been proven to be economically feasible under specific conditions for oil and gas fields and also for saline formations. You see, number 2 is use of carbon dioxide in enhanced oil and gas recovery. So you can see the 2 figure. So there the blue dot shows that carbon dioxide is injected so that it helps in terms of enhancing the oil and gas to be recovered. So it pushes the oil and gas so that it comes up. So that way it also is utilized in that way. And then coming to the third one, 3A and 3B. So A and B onshore offshore you can see on ground. So deep saline formation, wherever the saline formations are there, so you can see there the carbon dioxide can remain because both are having different pH. Coming to the fourth one is use of carbon dioxide in enhanced coal bed methane recovery. You see similar way wherever the coal has been recovered, okay, or has been extracted, so you have some gap or vacuum area there. So those places also this carbon can be injected, and there the gap is there, so carbon can be stored there. So these are the four options in terms of geological storage is concerned. Moving on to the oceanic storage options. So ocean storage potentially could be done in two ways. One is by injecting and dissolving the carbon dioxide into water column, typically 1000 meter via fixed pipelines, as you can see there. On the left hand side it is 1 kilometer to 3 kilometer, and beyond the depth has been shown. So pipeline is good up to 1 kilometer. So then 1 kilometer depth, then by moving ship, so you take it to ship, so ship will take it beyond and it will deposit via fixed pipeline or a kind of offshore platform that takes it to a lower depth, or you can say to a greater depth, to a greater depth, you can say 3 kilometer or beyond, so where the liquid carbon dioxide you can see is formed there. So dissolution type and the lake type. So where it is just forms a lake, we call it a lake type, and also it dissolves. When you release it, it dissolves because carbon dioxide is slightly acidic and the oceanic water is slightly alkaline. So that is why there is an affinity because of the variation in the pH level. So you see the lake type and the dissolution type. So these are the two ways the carbon is stored in oceanic reservoirs. Now moving on to the next one. So with this we discussed about the carbon dioxide capture and storage, CCS. Moving on to the next technology called the direct air capture. So friends, so in CCS we mostly talked about the CO2 capture from the point sources, that means industry sources or the sources where the carbon dioxide is very heavily emitted. But look at some other sources where lot of emissions is there over the urban areas from atmosphere because of the flight movement. So direct air capture is a crucial carbon dioxide removal technology for achieving net zero emission by balancing atmospheric CO2 release with removal. So it removes the carbon dioxide. So that means it serves two key roles. The first one is when integrated with carbon capture and storage, we call it direct air carbon capture and storage. It enables permanent CO2 removal to offset emissions from hard to abate sources like aviation. So this DAC is very well utilized in aviation sector because it is releasing and then and there it is removed. Second is when combined with carbon capture and utilization storage, we say the DAC CCU technology, it provides non-fossil carbon dioxide for producing the defossilized fuels and zero carbon chemicals. That means to fulfill these roles, the DAC or direct air capture systems must be scalable and economically viable. So what happens? A lot of studies have been done. So they often focus on assessing the solvent performance. Solvent performance, how it is observed. So under a limited range of weather conditions and limited period. So absorption is the main important criteria or the key in terms of directly capturing the carbon from air. And industrial scale, once it is done, it has to be done at upscale. So industrial scale deployment demands DAC systems with additional key features such as low pressure drop, high reliability for long-term periods in terms of years, and in a wide range of weather conditions. That means in various temperature, relative RH or relative humidity, moisture conditions, and also resistance to fouling from particles in air and without loss of performance by re-injection of carbon dioxide depleted air. So these are the challenges to make this scalable and economically viable. So once it becomes cost effective, then only people will, or it will have higher or the larger usage. Moving on to the taxonomy as far as the carbon capture is concerned, you can see it here, friends, the physical adsorption, the chemical adsorption, the chemical absorption. So two adsorption is the absorption at the surface, we know it. So physical and chemical basis. Coming to chemical absorption also, we have various technologies. And then coming to the membrane separation and electrochemical separation. So in terms of the physical absorption, you have the various technologies, you have the chemical ways, and also the absorption and the separation technologies. Now let's move on to the next one, which is integrated with bioenergy. So we abbreviate it as BECCS. So that is the bioenergy with carbon capture and storage. So what it is? That means, as we know, the biotic systems, particularly the plants, they help in terms of withdrawing the carbon dioxide from atmosphere. The plants, including larger plants, the algae and all those whatever who have the green pigment chlorophyll and do photosynthesis, they help in terms of withdrawing the carbon dioxide from atmosphere. So that means the technology, and the second component is this is integrated with the direct air capture and the CCS, that means carbon capture and storage technologies. So let us see the technology category as far as the CO2 withdrawal from the atmosphere by the biotic or the vegetation materials. So afforestation, reforestation, air, the soil carbon sequestration, SCS. Also the biochar technology, we know that, and also bioenergy with the carbon capture and storage. Then the direct air capture technology, enhanced weathering and ocean alkalization, or you said the EW, and the ocean fertilization technology. So this is put in two different ways in terms of two different color separations. You can see here it is involving both photosynthesis and the chemistry. So coming to this afforestation program, you see the implementation options. We have the agroforestry, boreal or agricultural practices. So you have different forest systems, the tropical, temperate and boreal systems. We also have different agro practices in terms of agricultural and the livestock practices. So this is there in the land, in terms of the land including the soil. Coming to the next is the crop residues, the dedicated crops and dedicated marginal crops. This is in terms of biochar, which helps in terms of generating the bioenergy. Then in terms of the DACCS, direct air carbon capture and storage technology, so suspended amines and wet calcination are useful in terms of, these are the implementation options we have, and the silicate rocks where we store the in terms of weathering and ocean alkalization. And moving on to the ocean fertilization, we know that the carbonate rocks and silicate rocks, they actually release the carbon dioxide, the carbon. Okay, they release the carbon which helps or which cycles in the ocean or the marine system. So it also involves the iron fertilization, nitrogen phosphorus fertilization, and also the upwelling in terms of upwelling dwelling in terms of enhanced or whatever variation in terms of the upwelling or downwelling process are concerned. So that deals with the oceanic chemistry. So the storage medium, as far as the carbon capture and storage through bioenergy is concerned, we store it in terms of AGB, above ground biomass, through photosynthesis route on the soil by not disturbing or or by managing the soil, in the geological reservoirs, in the minerals or the mineral carbonates, and also the marine sediments and the calcifers. So, in nutshell, the BCC is the bioenergy with carbon capture and storage is a negative emission technology. Why you say negative? Because whatever we are withdrawing the carbon dioxide from various sources, from various processes, that generates the energy, that means heat and power from biomass, while the capturing and storing the resulting carbon dioxide, removing it from the atmosphere. So that is how it is a negative emission technologies. It is distinct from direct air capture because it uses the biological photosynthesis to capture carbon first rather than chemical processes. So, using the biological system, it is captured first and then it is utilized in other ways in terms of storage. So, this is the beauty of the bioenergy with carbon capture and storage facilities integration, abbreviated as BECCS. So, these are the two references which have been used to prepare the slides. And what we discussed, friends, in general or in nutshell, we discussed about the carbon dioxide capture technology, particularly the components, various components of the CCS technology in terms of capture, in terms of transport, in terms of the storage, and also in terms of utilization by other industrial processes. So, storage also we discussed in terms of various geological and oceanic storage. We discussed about the direct air capture because CCS is different. It is from the sources where dominantly the carbon dioxide emission is happening, but direct air capture from other places where it is required to such as airplane and other aviation sectors. Bioenergy and CCS is a negative, carbon emission kind of system where it is withdrawn by the biota or by the plant systems. So, in this week we discussed the climate technologies. We discussed the technologies in terms of mitigation and adaptation. We discussed the engineering technology, or you said the gray technologies. We discussed the adaptation technologies, including the green technologies or whatever is being practiced as far as the nature-based solutions. We discussed about the cross-cutting technologies in terms of the geospatial technologies and the AI, artificial intelligence, and together the Geo-AI. And in this class, we discussed about carbon dioxide capture, storage, and removal technology through CCS, DSC, and BECCS. Friends, these are very, very important as far as the technologies are concerned to address the climate change impact, so as to realize the mitigation and adaptation goals or adaptation measures. Thank you very much.